Karen is here. Vanessa is here. Hannah is here. Good morning, Shelby.
That's how you do it.
No problem.
Sure. Okay.
Otherwise not working.
Okay, we've got 8:30, so why don't we get started? Good morning, Psych Stats.
Good morning.
Congratulations on making it through your first full week. It's quite an accomplishment. It was a difficult week, but we got there. And congratulations also on the many students in the room who made wonderful presentations yesterday in the Summer Research Symposium. I enjoyed many of the posters. I didn't get to see all of you, but I really appreciate the work that went into that. And one of the things that I tell my students all the time is this often repeated phrase, when I teach, I learn. And when you were engaging in your poster sessions the other day, or just yesterday, you were actually teaching your audience about what you had done. So this is kind of metacognitive because we can reflect on what it is you learned by doing that. There were several of you who were engaging in these poster presentations. How many people had a poster yesterday? Okay, so I wonder if you can tell us, when you were, just reflect on that a little bit, what do you think you learned by presenting your poster? And in particular, if you learned something about presenting your stats, that's fine, but you don't have to detail it that way, right? But in presenting your poster, what do you think you learned? It's very metacognitive. Okay, thanks, Jake.
I only spoke to like one or two people.
Okay. So you had very few customers. Okay.
Yeah, I didn't talk to a lot of people, but one of the women I talked with was just bringing up kind of alternate perspectives on like, mine was about power and posture, and she was trying to relate like emotion or some view that I hadn't necessarily thought of.
Okay.
She was asking questions about it and like kind of view things in a different way, I guess. Okay, all right. So because she had some questions that you hadn't thought of, okay, you thought maybe you learned something in that way, okay. Something else? We had a few folks who were presenting. Just maybe the act of preparing for the presentation. You know, what did you learn about that? We spend a lot of time in our psychology curriculum having our students make presentations. At the 200 level, everybody has to present posters. At the 300 level, everybody has to do a research talk, right? And that's a skill. It's really a skill, learning to do that well, and maybe get to understand how your audience will be seeing your research and where they might be lost, what vocabulary they might have and what vocabulary they might not have, okay? And the terms that you become very, very familiar with might not be familiar to your audience. You've got to think a little bit about how to present that. You also probably get some feedback while you're doing a poster. You get some visual feedback, maybe at their interest level, and that might prompt you to move things along a little bit more quickly, or you might see that they're confused but interested, and so you might choose to restate something or go over something or ask them about how they're doing. And you learn a lot of things about presentation and about what they're thinking when you're making an oral presentation in this almost one-on-one kind of format.
Okay? All right, so we'll have lots of opportunities to engage throughout this semester teaching each other in sessions that we'll call When I Teach, I Learn. Before we get into something like that today, though, I did want to make sure that we just had our eye on what's due for our next session. So this is Friday. We're coming up on a Monday session, and all of our Monday sessions are journal club sessions. And this particular journal club session I think will be fun because I was teaching this course 10 years ago this semester, and one of the students in your seats was Zach Daniels. And Zach Daniels is now a biostatistician, and he is one of the authors on the article that you're going to be reading. So he's a graduate of not only this college, but also of this course, and we'll have another TED Ed to do on that. And this particular journal club session will only be the first 30 minutes of our 50 minutes together. Melanie will be doing a presentation for us, and we'll give Melanie the option of having herself recorded, and the same thing for all of you. When it's your turn to make your presentation, you can be recorded. And one other thing I don't think I've mentioned before, Melanie also gets a break on the TED Ed questions. You are exempt from the TED Ed questions for that. So when you're doing preparation for a session, why don't we make the rule this way? For a journal club session, either you're making the presentation, so you're kind of on for 15 minutes, and then we'll have 5 minutes of discussion after that. So you're on for the last 20, but you're really speaking for the first 15 of those 20. The first 30 minutes of the entire 50-minute session, though, will be our TED Ed session, in this case on Zach Daniels' article, and we have those TED Ed questions for you. So the rest of us can stay on that, and you can play along with us, too, during that session. You're not excluded from it, but you don't have any responsibility. Okay? The rest of us will complete those questions by 9 p.m. on Sunday night, and that'll set us up very well for a good conversation. And we'll be back there as we always are on Monday. Who's okay with that? You understand? Okay, that'll be our rhythm. We'll typically make that announcement on a Friday. Okay. Any questions about any of that? Or about the poster session? Okay. Why don't we then go ahead and just warm up a little bit with one of the items that we were talking about yesterday. We were talking about moments in descriptive statistics. So can somebody help us out with what are moments in descriptive statistics? I spent a fair amount of time on that yesterday. Okay, thanks, Vanessa.
It describes the shape of the set of points.
Okay, right. It describes the shape of a set of points, right? And frequently the set of points will be a frequency distribution. Very important to descriptive statistics. Okay? Can somebody tell us about some of the different kinds of moments that we have? I think we described 4 of them on a regular basis, and then you can go to higher order ones, but we semi-frequently will use these 4, the first 2 especially. Thanks, Gabby. One of them is kurtosis, okay? Right? Does anybody remember which of the 4 it was when we think about the exponents? We talked about how you can describe all the moments by taking sums of exponents. Does anybody remember what the kurtosis exponent was? Yeah. That was the 4th exponent. What was the 3rd exponent? That corresponded to which of our moments or shapes of the distribution or characteristics of shapes of the distributions? Our 3rd moment was, skewness, okay? And the first 2, arguably the first 2, are mean and standard deviation. You could say that there's a 0th moment, which is simply the sum, they might call that the mass of that set of points. Okay, so we were using those, and then we were frequently making comparisons between different kinds of moments of different kinds of frequency distributions, and then also Gaussian distributions. And when we introduced Gaussian distributions, that brought us over to z-scores. So can somebody help us out with just that big picture idea? What is a z-score? Okay, yeah.
It's like a way of saying how many standard deviations away from the mean.
Excellent. It's a way of we can use z-scores to describe how far away something is from the mean. And so in a sense, it's a measure of dispersion, which might be our 2nd order moment, okay? And it's tied to the standard deviation. Okay. Can somebody remind us how we compute a z-scores? Anybody recall the formula off the top of your head? Yeah, thanks. Victoria.
So the z-score equals x or raw score minus the mean divided by the standard deviation.
Okay, so we start out with some kind of a raw score, we subtract from that the mean, and we get a different score, and then we divide that different score by the standard deviation for the distribution from which that score came, okay? And then you can turn that around algebraically, and you can go from a z-score to a raw score. We can go back and forth. We can also go to percentile ranks, and we spent some time doing that. Why do people find z-scores powerful? Why do statisticians find z-scores powerful and useful? Gabby? Okay, you can compare things that are very different from each other, that are on different scales, that are measured in different dimensions, maybe weight and height, or maybe reaction time, and some other kind of arbitrary measure like a physical attractiveness score or an IQ. Right? So you can go from an IQ to a reaction time or to a height. Right? You can compare apples to oranges because you're now in this dimensionless unit on the assumption that we do have a Gaussian distribution. We don't always have Gaussian distributions, but many things are Gaussian distributed. And yesterday we also had some fun factoids about Gauss himself. But once we have a Gaussian distribution, we know a lot of things about relative percentiles, and we can use z-scores and so forth. Okay? All right, so what I wanted to do this time around is pick up where we left off on the TED-Ed questions for z-scores. And I think we got up to maybe question 11 or so. Let me dial into our z-score session. Okay, and let me go to just an arbitrary student. We'll do a few of these and then we'll go off to today's psych stats. So let's go to, I don't think we've looked at Shelby in a little while. And I think we left off maybe at question, let's see, question number 11 or thereabouts. Okay. Okay, so the so-called standard normal distribution is a Gaussian distribution with a mean of 0 and a standard deviation of 1. In the standard normal distribution, what percentile rank is associated with a z-score of -2? Well, maybe we ended with that one yesterday, okay? And I think Hannah told it. I think you had the answer at the end of yesterday's session. Do you recall what that was? Or do you need to see it again when you see the distribution? Okay.
2.3 for the
So, okay, so, actually, a z-score of -2, right? A z-score of -2. Okay, so we want to go, here's the center of the distribution, we want to go this way, and then that way, 2 steps, right? 2 z-scores down, okay? And I actually don't have it right in front of me. Can somebody tell if you found that, that value on your Gaussian distribution, okay? It's going to be really small. It's going to be in the single digits. It might have been 2.3. Is that the one that you had? Okay. Okay, very good. And then if it was -1, do you remember what that was? Z-score of -1, what's our corresponding percentile rank? Approximately? 34 is an important number to have. Let's start at 50. Let's go, so 50% of the distribution goes from way over here up to here. So far, so good. We're going to go 34 percentage points back from that. And 50 minus 34 puts us at 16. And I think Hannah had 15.9 might be the actual computation there, right? So if we're 1 z-score away, we're on the lower end, right? On the negative side, we're going to be at the 16th. And then if we're 1 z-score beyond that, if you have the distribution in front of you, it's going to be something like 2% or something of that order, okay? Okay, let's see if we can get into something a little bit more conceptual. Okay, a function is a rule for turning one number into another number. Excel's norms in function allows you to input a probability and or a percentile rank so that you can find the corresponding z-score. Okay? All right, did anybody do this one and try to find the corresponding z-score for the 75th percentile? So you would put in a 0.75. Okay? What did you get out? And you can do this now in Excel if you want. If you want to call up Excel, if that helps you. Go to any one of these, really. Okay? And we can take a look again at that syntax. Okay? This was the norms inv, okay, equals norms inv. So we'll go over here. Equals, and the norm stands for the normal distribution, right, or the Gaussian distribution. The standard, the S stands for the standard distribution, which has a mean of, let's all call it out. The standard distribution has a mean of 0 and has a standard deviation of 1, okay, right? So that's one of the many kinds of Gaussian distributions that we can have, okay? Put in an inv, okay? And we said we wanted the 75th percentile, okay? So 0.75, okay? And that gives us this percentile rank, right? We can say that we are, I'm sorry, it gives us this z-score, 0.67, okay? So it gives us a z-score of 0.67. And then we can also do the same exercise by putting in a 0.25. Okay, why don't we try that? Put in a 0.25. So equals norms inv, And the parenthetical value, that's the one that we're going to insert, is going to be 0.25. What did we get? Yell it out if you got it. Okay, you got a 0.67? A negative 0.67. Okay, negative 0.67, okay? So same number, but different signs. Why would that be the case? Somebody help us out with that? Why would we get the same number, but a negative? Yeah. Okay, thanks.
75th percentile and the 25th percentile are equal distance from the...
Okay. Okay, yeah, maybe it's helpful if I go back and find this slide that we had the other day, and we'll project a nice picture, maybe from Wiki, put in standard score, or z-score. Okay, here's the guy we want to be looking at, okay? So here's our Gaussian distribution, here's the 0 z-score, and if we take a certain distance away from 0 on this side, and we take that corresponding distance on that side, right, we should have very similar z-scores or percentile rank distances from 0 or from the 50th percentile, right? So if we're at the 75th percentile, we're up 25 percentile points, and if we're at the 25th percentile, we're down 25 percentile points, okay? And we can convert those into z-scores. This would be the z-score distance in a positive direction, which was positive 0.67 and some change, right? And then we can go that same distance down 25 percentile points from 50 down to the 25th, and now we're at minus 0.67, okay? So it would be plus 0.67 minus 0.67 on z-scores. Who's following that? Is that working? Okay. Now, that's one of the nice things about having a perfectly symmetrical distribution. And often we assume a perfect Gaussian. Rarely do we actually get a perfect Gaussian, but it's actually a pretty good approximation for many of the things that scientists measure. Okay? Okay, so those were that pair of questions in TED-Ed. Okay, and I think question 13 asks us to think about that comparison. Question 14 did. Let's go on to question 15. A function is a rule for turning one number into another number, and here we have the norms dist function, allows you to input a z-score, okay, so that you can find the corresponding probability akin to a percentile rank. So what percentile rank corresponds to a z-score of positive 1? Can somebody help us out with that? We'll let you use Excel as you need to. And if you get that, I'll let you raise your hand when you get that answer. Okay, so several hands are up. Okay, so again, we're going to be in Excel. We're going to put an equals norm. Norm stands for the normal distribution. That's the Gaussian distribution of the bell-shaped curve. There are different varieties. You can have all different kinds of Gaussian distributions. They're all Gaussian, but they have distinct means and standard deviations. The standard one has a mean of 0 and a standard deviation of 1. And we're going to use the distribution function where we stick in a z, and we get out some kind of percentile rank. So we stick in a positive 1, and what do we get? 84. About 84? Okay, right. Okay. Can we stick in a negative 1 and see what you get? Yell it out when you get it. 16, okay. So just to see what that's all about, we started out, we can always think about starting out in the center, okay. If we stick in a positive 1 z-score, that's 1 sigma. Remember that sigma is a population parameter, and we can have positive 1 standard deviations above that. If we take the first half of this distribution, that's 50, we add 34 to it, we got 84 a moment ago, right, or the 84th percentile. It might have been expressed as a 0.84. And then if we go down 1 standard deviation, we can start all the way on the left and up to here. And that's, if we sum all of those, we're going to wind up to something like 16%. You can think of taking 50 and subtracting 34-ish, and that'll put you at about 16%. Okay? Does that work for us? Okay? Real good. Real good. Okay, so that's our little introduction to z-scores. Questions about any of that? Okay. Now, the reason that's important is that first we can, as we said a moment ago, we can compare different kinds of scores to each other using z-scores, but also we've become very familiar with a frequency distribution, and we understand something now about areas under the curve. Particular percentile ranks might correspond to particular kinds of scores, like standard scores or z-scores. Okay? Now we can think about other kinds of distributions that we might be using for hypothesis testing. Okay? So we'll go over to our hypothesis testing bit. Okay? But just before we do that, I'll give us one more little summary on all of that. Okay? This is a slide that I've put out on the S drive. I'll just walk you through it. We won't spend too much time on this now. But this is a little summary of the z-score exercise that we just did. And it's also a great way of sort of setting the stage for other functions that we might be using. Okay? So these were z-score related functions in Excel. We used one called normsinv. We used one called normsdist. Okay? And our mantra that we'll have throughout the course is going to be that a function is a rule for turning one number into another number. Okay? So it's right up there. Can you say it with me? A function is a rule for turning one number into another number. It's a gumball machine, right? That's what a function is. In a gumball machine, we stick in a penny, we get out that gumball, okay? Same kind of a thing for a function. We stick some number in, we get out something else, we get out another number. We might stick in a z-score, we get out a percentile rank, or you could do that backwards, stick in a percentile rank, get out a z-score. So there's the function and its inverse function, okay? So we have these function names in Excel. We just played around with these first two, right? Norms, and this stands for what? What does norm mean? Normal distribution, which is also called a Gaussian distribution, okay? The S tells us what? It's a standard, which means the mean is 0 and the standard deviation is 1. Okay, and then we have the dist function and the in function, very similar to each other, except one takes in a z-score and spits out a probability or a percentile rank. Okay, so if I put in a 0 z-score, what would my percentile rank be? Can we think about that? Yell it out. If I stick in a 0, my percentile rank is going to be 50. Okay, because that's half the way through, right? Okay, so put in a penny, take out a gumball, okay, or get out a gumball. You can imagine doing, the inverse of that. I stick the gumball back in and I get my penny back, okay? So we can now do a similar kind of distribution. It's also a Gaussian distribution, normal distribution, same kind of mean and standard deviation. We'll do the inverse though. Now we'll stick in something like a 50th percentile, and we should get out a z-score of what if I stick in the 50th percentile? 0, okay? If I stick in a percentile rank of 0.84, or the 84th percentile, put it that way. Okay, what would I get out as my z-score? 1, okay? If I stick in a 0.16 or 16th percentile rank, what would I get out as my z-score? Okay, all right. So you get the idea. Right? These other functions over here are simple variations on this. What you might notice is that almost everything's the same for these bottom two. I suppose it's the case for the top two. But now we've taken the S away. Okay? So now these are still normal distributions. Okay? And again, this is all out on the S drive in case you don't have to call it up now, but you could if you wanted to. You don't have to take it all down. And here again, it'll be now the norm dist. It'll work very much like this guy does, the one on the very, very top, but it allows us to stick in our own mean and standard deviation. Okay? I'll come back to cumulative in a moment. So what I could do is I could stick in a mean of 0, and I could stick in a standard deviation of 1, and then this would be operating exactly the same way as the standard normal distribution would be operating. Who's following that? Does that work for us? Okay. But it might be the case that you're a psychologist or some other type of scientist, and you've got a Gaussian distribution that doesn't have a mean of 0 and a standard deviation of 1. So the IQ distribution, does anybody recall what the norms of that typically are? The mean and standard deviation for the IQ distribution? Yeah.
The mean was 100 and the standard deviation was 15.
Okay, the mean was 100. Okay, that's the mean IQ. And then there's a standard deviation of 15 points on that. Okay, so I can use this function, and I can basically use it as my gumball machine. I might need to be able to jump back and forth between z-scores and something like percentile ranks. Okay, and what I can do is I can put in a mean of 100. That's my average IQ, and a standard deviation of 15 IQ points. Okay, and now it operates really the same way. It's still a Gaussian, but I was now in this case able to specify my own mean and standard deviation. Who's following that idea? Same thing is true over here for the in function. We used to put in a percentile rank. We'd put in a 50th percentile rank. We'd get out a 0 z-score. We can do the same thing over here, but we get to specify our own mean and standard deviation. Okay? All right. Then there's this idea about the cumulative curve or the non-cumulative curve. So can we all draw a bell curve in the air? Let's go ahead and draw your bell curve. Okay? So it begins to accumulate, and then all of a sudden it doesn't accumulate anymore. It comes back to 0. It is non-cumulative. Can we try this? We tried something like this yesterday. Can we take that same bell curve, but instead of drawing a non-cumulative bell curve, which is what that typically is, we'll draw a cumulative Gaussian. What would that look like? Okay, and we had a few people drawing that. Okay, so what you can do is you can specify whether you want the output to be taken off of a cumulative curve that goes up and up and up monotonically, was a word that we introduced yesterday. Okay, or you can leave that value as a 0, and that will say, no, we don't want the cumulative type, we want the standard type. Okay, and we get this type that rises initially and then falls back on itself. Okay, okay, so sometime, if we have a little bit more time, we can dive in and play around with these. As a matter of fact, why don't we take just a moment and we'll play around just a little bit with a norm dist and a norm int. So can you open a blank sheet anywhere in Excel? And we'll just do a couple of these. Okay? So you get the hang of it. It also gives us an excuse for playing with functions, because we're going to be using lots of functions throughout the semester. Okay. So somewhere in here, let me just make sure everybody's on Excel. How many people have Excel open? Okay, that works. Okay. Anywhere that you want. Why don't we do the norm dist function first? Okay. So I put the word norm dist here on. It doesn't really matter which cell. I happen to be in C4. Okay. And then why don't we get our labels right? Why don't we say score in the cell next to it? We'll type in the word mean in the cell next to that. We'll type in SD for standard deviation and any abbreviation of cumulative. This idea about whether the curve builds on itself or falls back down to 0. Okay. And if you want, you can highlight a couple of cells, maybe a rectangular patch, and you can center that just so it's all nice and neat. The center button is up here. Some people are very familiar with these, others less so. Okay, so we center that. We'll come back over to here. Okay, and now we'll type in equals norm dist, and we'll open a left paren. Okay, equals norm dist, and we'll open a left paren. And once you do that, you can see that Excel says, okay, you've told me you want to start operating with this particular kind of gumball machine, this function, this rule for turning one number into another number. For me to work, I need these 4 pieces of input. I need some kind of a score, okay, whatever that score might be. I need a mean, I need a standard deviation, and tell me yes or no whether it's cumulative. No is 0, 1 is yes, it is cumulative, 0 is no, it's not cumulative. Okay? Okay, so just for the moment, we can put in something like, how about this? We'll say that we're going to make the score equal to whatever is over here in cell D, what would that be? D5. Okay? So I can put that in. Then I can say I want the mean to be whatever equal to whatever the value of cell E5 is. Okay? And if you're not in column 5 or column D and E, that's okay also. You can make this appropriate to your own sheet. Okay? And then we can continue and say that we want to use F5 and G5. Okay? Okay? And it might be the case that you get nothing, you get some kind of number error there. But you can put in these numbers. You can put in a score of 1. Okay? You can put a mean of 0, a standard deviation of 1. And we'll say yes, cumulative in this particular case. Okay? We'll let you catch up with that. Okay? And we'll let somebody just unpack what this is. Okay? So what is this function telling us? And why is it giving us a 0.84? I'm going to start even more broadly. How many people have got that? You've got it all keyed in? Okay, so it's doing that. Okay, that's a 0.84, and the score that we put in was 1. Let's pretend that's a z-score. Let's pretend it's a positive 1. Okay, why would we be getting an 84 out of this thing? That's number look familiar? Hopefully in a stats class, the 84 should ring a bell, and ring a bell curve. Okay, yeah, thanks.
It's just one standard deviation.
Okay, right. Okay, so our score was 1 standard deviation above the mean. Okay, right. Did you get that, or are we still okay? Okay, so let's, if you'll just bear with me, we'll make sure we get the syntax right. So Vanessa, we're going to do this. If we're over here, we're going to say equals norm dist. Okay, and then we'll say left parenthesis. Okay, does that work? Okay, right. And then what we're going to do is we're going to let the first value, which is called the score, equal whatever in cell D5. So here's cell D5. Okay? And then we're going to say we'll let the next parameter, which happens to be the mean, we'll let that be equal to 0 and so forth. And we need to fill in those 4. Okay? So Jake is onto something here, that we can say that if we put in a z-score of 1, and we have a mean of 0, standard deviation of 1, and it's cumulative, we should get to 0.84.
Yeah, did you say something about centering it? What was that?
Oh, so all I was doing was just changing the format of this. I clicked on this and I went like that. Okay. Okay, and this is, you have norm dist, not norms s dist, right? Norm dist. Okay. Okay. Let's try this. Let's put in a different kind of a score. Let's put in a 0 and see what we get. Okay. And can somebody again just, let's all yell out, why does that make sense? If I have a score of 0, why would my norm dist be 0.5? It's the mean, and the mean also is the 50th percentile. Okay. Okay. How would I turn that into a well, you tell me, if I were to put in a -1, what would I show in the norm dist? I put in a -1 for my score, okay? I should wind up with what kind of percentile rank? About something that approximates 16, okay? And it won't be exactly, so we use 16 as an approximation, but it's actually 15.86 and some change and all of that, okay? Okay, let's see if we can fool around with this now. We'll go over to the mean, and let me just check in. How are we doing? Not yet? Okay. Okay. How about this? You don't have to put in all these different items. Just say equals norm dist. Okay. And can you then put it in a left paren? -1, comma, 0, comma, 1, comma, 1, right paren. What'd you get? 0.158. Okay, so basically, that's good. But you've literally put into these 4 slots the numbers that we're extracting from these 4 positions. Okay, this is how we built that. Okay. Okay. What happens if we change the mean to 100, the standard deviation to 15, and the score to something like 115? Can somebody help us out with what's going on there? Thanks, Victoria.
This is the distribution for like IQ.
Okay. Okay.
The mean 100 with standard deviation of 15.
Okay.
So a score of 115 is 1 standard deviation of the mean, so 84%.
Wow, perfect. Okay, that was a lot. Okay, but let's see if folks can follow her logic. So what we did was we decided to use a Gaussian again, because we're still using the norm dist function, but now we're not using the norm s dist, we're using the norm dist. We get to specify our mean and our standard deviation. To put on our training wheels a moment ago, we used a 0 and a 1, but now we can think of other kinds of distributions. One that's fairly easy to think about is IQ, mean of 100, standard deviation of 15. Hopefully you can do the math in your head that if we take 100 and add 15, that's 115. So this person is our 1 standard deviation or 1 z-score above the mean. And I might be able to find that again. Here we are, okay. So here's the 50th percentile. We went up by 1 standard deviation. If this were the IQ distribution, we'd be at an IQ of 100. We'd be at an IQ now of 115. We add all that up. There's the first 50. There's another 34-ish%. That puts us at the 84th percentile. And that's what we're seeing here. Go back over to this, excuse me. Okay, that's what we're seeing here, okay? So, you can play around with other IQs. So, let's just see where I land. What did we say my IQ was yesterday? Anybody recall? Let's see if we can do this bit in our heads. So, my IQ is 4 standard deviations below the mean. What is my IQ in raw scores? Okay, 4 standard deviations below. So it's going to be 4 z-scores below. My IQ is 40, okay, right? So where do I land in percentile rank if my IQ is 40? So I'm way down there, right? Haven't even gotten to the first centile yet. Okay. But if my IQ were 4 z-scores in the other direction, okay, I'd be in, like the 99th percentile. That's where that's going. Okay? And people are following that? Is that working for us? Okay. Okay, so you get the idea about using functions, and again, here we have our summary. Oops, excuse me. Okay. The function is a rule for turning one number into another number. We can use these to go back and forth on normal distributions. Okay. All right. let's go back to TED Ed and start talking about some of the issues that you were looking at for today. Unless somebody has other questions about that Excel exercise, we'll go over to TED Ed and we'll start talking about hypothesis testing. Right? Now we know a lot about different locations on a frequency distribution. That's going to be helpful for testing statistically what is significant and what is not significant. Okay. Okay, so let me go to a different kind of layout here. Okay, here's hypothesis testing. Okay, and let me just go into any one student randomly, and we'll take a look at some of the responses that we've gotten. Okay, to question number 1. Okay, why is it that statistical hypotheses are stated in terms of population parameters rather than sample statistics? 1 or 2 sentences would be plenty. Can somebody help us out with how they responded to that one? Population parameters. Thanks, Hannah.
I said the purpose of a hypothesis testing is to make inferences about a population.
Okay.
From the sample.
Okay.
So if you're just describing the sample only, then you can make this.
Excellent. Okay, so we do have this big idea of the population. We take a sample for practical reasons, but when we're describing the mean and standard deviations of those two entities, we would use a statistic to describe the mean and standard deviation of a sample and a population parameter, like mu or sigma, to describe the mean and standard deviation of the population. And we're trying to draw an inference about the population in inferential statistics. Okay, so we're going to be using population parameters for that reason. Right, let's keep on moving here. Think of any classic finding in psychology. I really enjoyed writing this question because it makes me think back to Intro to Psych and all the different things we learn about in Intro to Psych, sort of the greatest hits of Intro to Psych, okay? And generate a null hypothesis that this classic finding might have rejected and be creative. So let's get to think that through, and maybe somebody has an example that they want to share with us. There's a lot going on there. You have to harken back to a classic finding in Psych 100, okay, from the history of psychology, and then almost restate that finding in terms of a null hypothesis that was being falsified. So thanks, Gabby.
I chose the Bobo doll experiment.
The Bobo doll experiment. Okay, and just for context, how many of us have heard of the Bobo doll experiment? Okay, is that everybody? Okay, all right, real good. So, yep.
The null hypothesis would be children in both groups group seeing the aggressive adult and the group seeing the non-aggressive adult, and not act different towards the adult in the experiment.
Perfect. That was right on. Okay, so in the Bobo doll experiment, we're trying to see to what extent there's such a thing as social learning, and so we can have the half of the children exposed to a model who's really punching the Bobo doll or acting aggressively toward it. The other half are the students are exposed to adults who's maybe not showing any kind of aggression, and then we're going to look at the kid's behavior. How does the kid respond to the Bobo doll? Right, okay? And the null hypothesis would be that there's no difference in behavior between those two groups. Okay? Very frequently, when we write a formal null hypothesis, we start out with this prepositional phrase, and will be maybe our favorite prepositional phrase of the entire semester, which is in the population, comma. Okay? Let's all say that together, in the population. In the population, comma. And then I'll paraphrase what Gabby said a moment ago. There will be no mean differences between the children exposed to aggressive and non-aggressive adults. Something along those lines. Is that a fair paraphrase of what you had? Okay. And so then we do the Bobo doll experiment, and we find that the kids who are exposed to the aggressive adults really do beat up on that Bobo doll, much more so than do the other kids. We can get graphs of those differences, and we can wind up rejecting the null hypothesis, right? Because the one group is going to have a z-score that's very, very different from that of the other group. And it's going to be so far out there that it might be in the critical region, we can reject the null hypothesis. Okay? Here we got one or two other examples from psychology's classic history that we can rephrase as a null hypothesis. Okay, Jake's got one.
Based one off of Ash's conformity experiment.
Ash's conformity experiment. Okay, who remembers hearing about Ash's conformity experiment? Okay, this was in the domain of social psychology. Who's not sure they remember hearing about that? It's okay if we don't recall necessarily hearing about Ash's. Okay, can you say a little bit about that?
I think the experiment asked participants to say which line. There were like 3 different line options, and you guess which one like matched the line.
Okay.
And there were Confederate participants who just obviously picked the wrong answer, and they didn't see actual participant.
Yeah, right. So it might be something like, which line is longest? Okay. And the correct answer is B, right? Okay. But everybody in the room is a Confederate, and poor Karen is our participant, right? And so we go around the room and say which one is longest, and everybody should be saying B, but they start saying something really crazy like C, okay? And then the question is, what does she do in the presence of that conforming influence, okay? Okay, so that's the experiment. Who's following that? Is that working for us? Okay, so it's a social psych experiment. They tried to make it look like as if it were an S&P experiment, where you're judging some kind of perceptual response. But really, the manipulation is one that's a social conformity effect. And so can we state this as a null hypothesis?
Yeah, it said these findings would have rejected the hypothesis that in group situations people will not conform to people.
Excellent. Yeah, right. So there's a not in there, right? There's going to be a not in our null hypothesis. And we might say something like, in the population, there will be no difference between those who are exposed, no difference in responding between those who are exposed to the conforming influence and those who are not. Okay? Okay. So I think we get the idea. Right? Okay, why don't we go on and see what we get for number 3. Okay? Give an example of a relatively liberal alpha level and a relatively conservative alpha level. Explain your answer in 1 or 2 sentences. Anybody want to help us out with that? It's an interesting way of thinking about alpha levels, liberal and conservative. It has nothing to do with the way we use liberal and conservative in our political conversations. Okay, Sarah's got something.
I said for the conservative alpha level, it would be something like 0.001.
Okay.
And a more liberal alpha level would be 0.05.
Okay.
Because the 0.05 isn't as strict, and so it allows more room for type 1 error than the 0.00.
Excellent. Beautifully stated, okay? And that might be review for a lot of folks, but just to make sure we're all on track with our vocabulary, the idea is that 0.05 will allow it will allow 5% false positives, okay? And 0.001 will allow 1 in 1,000 false positives. Okay, that's the idea there. And the more you allow false positives, the more liberal you are in making your judgment in rejecting the null hypothesis. So we have a relatively easy criterion for rejecting the null hypothesis, or a stricter criterion for rejecting the null hypothesis. Okay, maybe we'll do one more before we get into some of the Latin logic. I'm curious to see what people did with the Latin logic. Okay? So careful scientists often use phrases such as, we reject the null hypothesis, or we fail to reject the null hypothesis. Why don't they instead say, we have proven the alternate hypothesis? They avoid using the word prove. They typically say reject or fail to reject. And in everyday life, and frequently in Psych 100, when the students are coming in, they say things like, scientists demand proof, and the scientist proved her point with this data set, or something like that. But actually, trained scientists refrain from using that. They say reject or fail to reject rather than prove. Can somebody help us out with why we choose that terminology? Yeah, thanks.
You're not actually proving your research hypothesis. You're just proving that there's a very low chance that that the results were caused by something other than.
Okay, yeah, right. And we might say we're providing evidence for the relative probabilities of these things, right? Prove is a level of statement that's too strong, right? It's just we don't have the evidence to say something is unequivocally true. We understand things here statistically. Things are probabilistically true, okay? Or things are have knowable likelihoods and so forth, okay? So to use the word prove is too strong. There's another reason for this, and this brings us to question 5 and the ensemble of maybe questions 5 through 10, where we start getting into this Latin logic. Just by a show of hands, how many people had seen Modus Tollens before? How many people had not seen Modus Tollens before? And I'm not sure whether this version of our book, we get new editions of the book every couple of years. I don't remember if this appears in our readings or not, but hopefully you're able to go out there. And so in your own words, can somebody briefly explain to us what Modus Tollens is? If you consulted the wiki on this. Somebody want to help us out with that? Okay, thanks, Melanie.
So basically my understanding of it was if like a conditional statement is true, then it's like contrapositive is also true. So
Okay.
if P then Q, if that is true, then if not P, then not Q is also true.
Wow, okay. If P, then Q. Right? That's the first bit. And she used the phrase conditional statement. And when we say conditional statement, that typically means just this much. It's a statement that starts out with the word if. If this thing, then that thing. It's usually an if-then statement is our conditional. So if P is true, then Q is true. Right? And then we do an empirical investigation. As you'll see, this is going to be kind of like our null hypothesis. If there's no effect of social influence, then we would expect to see that people who are in the social influence group and those who are not will have the same behavior over here. If there's no effect for Bobo doll exposure or no effect for exposure to aggression, we would expect that the children in the Bobo doll aggressive group and Bobo doll non-aggressive group would behave the same way. If P, then Q. Then we actually go out and we collect our data, and let's say that we find out that Q is not true. Okay? And the way that sometimes we signify that is by this. That little squiggle is the not sign, so that means not Q, or Q is not true. Okay? Therefore, we need to draw a conclusion here. If P, then Q. Not Q, therefore, can you finish it for me? Not P. Okay? So this is basically the logic of hypothesis testing. Right? If the null hypothesis were true, then we should get some kind of maybe a p-value that's greater than 0.05. Let's say we run the Bobo doll test and we get a 0.0001 p-value. Okay? Then it's not the case that the p-value is greater than 0.05, the p-value is less than 0.05, then the null hypothesis is not true. Okay? If P, then Q, not Q, therefore not P. So that's actually the formal logic that underlies all hypothesis testing. That may or may not have been laid out for you in Psych 200, but this is what you were actually doing in Psych 200. And professional logicians who study propositional logic will tell you that this is a valid form of reasoning, and the valid forms of reasoning frequently get a Latin name, and this one happens to be called Modus Tollens. Okay? So our reasoning in hypothesis testing is based on this. Who's following that? Okay? Another simple example, I use this one all the time. If it rains, then the street is wet. We go out and we make an empirical investigation. We see that the street is bone dry. Okay? So the street is very dry. The street is not wet. Therefore, it didn't rain. Okay? Is the idea there. Okay? All right. Let's go to some variations on that. We've already done how does null hypothesis testing relate to modus tollens. Let's go over to here. Let's skip a little bit. Let's go into some of the errors. How does modus tollens differ from the logical fallacy known as affirming the consequent? Okay? And this is tough. So anybody want to take a shot at this one? Thanks, Melanie.
So I basically use an example to kind of explain the difference between the two. So
Okay.
I said that with modus tollens, like if we deny the consequent, then we can conclude that the antecedent also does not hold true.
Okay, and that was perfect, and I'm going to stop you right there because you've introduced some important terminology. Okay? So in this very simple statement, if P, then Q, this one comes first, P is coming first in that statement, Q is coming later in that statement. The one that comes first we call the antecedent. Okay, we call that one the antecedent, okay? And we call this one the consequent. And that's fairly intuitive, right? Because we can say that this is a consequence. This is what comes later, okay? So here's the antecedent, here's the consequent, okay? So sorry to interrupt, but you gave us a really great start on that.
But if you affirm the consequent, you can't necessarily conclude, you can't really infer anything about the antecedent.
Okay.
So I use sort of an example of, for my if-then statement, if an individual exercises at the gym, then they will be sweaty.
If they exercise at the gym, then they're sweaty, okay? And then
so
we go
I
and
said
yeah.
that if a person is found to be sweaty, it does not necessarily mean that he went to the gym.
There could be alternate explanations.
Yeah, he could be sweaty from some other activity.
That's right. He could be sweating because it's really humid outside, or because he's really nervous, or something along those lines. So you can't go to this antecedent by affirming that consequent. Okay, you might get lucky. Okay, it might be the case that this person is sweating, and they are sweating because they happen to be working out at the gym. Okay, to stay with your example, but you can't necessarily go from here to here. Okay, so we don't look at affirming this. We typically set up the null hypothesis and see if we can refute it. Okay, and we refute it using Modus Tollens, which is denying the consequent, not Q. Okay, a very different move than saying, we observe Q, therefore P must be true. Okay? Who's following that? Okay, is anybody confused by that? That's a lot. It's kind of abstract. Right? Okay. All right. So that was a lot to think about, and some of that wasn't in the reading, so thank you for going out to the wiki and doing that and setting up the logic of hypothesis testing. Why don't we give you 1 minute off for good behavior? Okay? I look forward to Monday's session. So we'll have Melanie making our first presentation, and for the first 30 minutes we're going to be doing our article written by Zach Daniels and a little bit on genotyping and responsiveness to different kinds of drugs and different kinds of behavioral interventions. Okay, have a great weekend.